The webinar today will be on HILIC, and this is a very interesting topic, and it's a topic that I talk to many chromatographers about, and there is a degree of difficulty with understanding how to develop HILIC separations, reproducible HILIC methods. And so this webinar, I hope, will help you practically with some hints and some tips based on data and examples generated in our lab. And also at the end, there's a very brief step-by-step approach to developing a HILIC method, including a method development protocol, which I hope you find very useful. So firstly, I'd like to say thank you to VWR for organizing and establishing this webinar series. I hope that you all find this useful. As Ian said, the slides that I'm going to present now will be made available after the webinar has completed. I'm going to begin by doing a poll just to understand from the audience, as you sit there now, how many of you actually performed HILIC separations. So if you can, click, if it's possible, on your screen just to register your vote. Then that will help us have an idea about how many of you are brand new to the technique of HILIC, and maybe there's some experienced practitioners out there as well. So as Ian said, my role is developing separations and new products and technology for advanced chromatography technologies, and HILIC is one of those areas that's got very popular over the last few years. And with us releasing our own products last year in this area, and we've also written a considerable amount of what we think is useful material, practically useful material, to help practicing chromatographers to see if we can help you develop your methods that you're trying to solve with the problems you have in your lab every day. So without further ado, I shall move on with the presentation. So this presentation is split into two parts. First of all, I review some of the basics. So first of all, what is HILIC as a technique and when should you consider it? As separation scientists, we're challenged with problems every day, separating different analytes in different matrices. How do we know when we should consider HILIC as a technique, when maybe reverse phase or ion exchange or even GC and other types of techniques may not be appropriate? So I'm going to cover some of those points today. What are the advantages with HILIC as a technique, but also, just as importantly, what are the disadvantages? What are the things we should watch out for? I'll also speak about some of those. I'll talk about different types of HILIC columns that are available. Again, speaking to many practicing chromatographers and scientists around the world, it's interesting that many people don't realize the different types of HILIC columns that are available, and I'll talk a little bit about that today too. When we consider HILIC mobile phases, what are the composition of these mobile phases? Why are they based on the different solvent systems that they are based on? Why is that? And I'm going to talk a bit about that today too. And then a variety of hints and tips are topics I'm also going to cover. And there's probably two topics which I think float to the top of being the most important for HILIC as a practicing chromatographer that you need to consider when you're using HILIC as a technique, or if you're developing HILIC methods. First of all is column equilibration. This is an important subject, and it's something that's quite different to reverse phase chromatography, which many people are familiar with. And I will go through some of that in detail. And then secondly, sample diluent. So many chromatographers use a variety of different diluents and solvent systems when they're developing their methods. Now, HILIC is a technique that we need to have different considerations, and I'll cover some of that today too. So, what is HILIC? So hydrophilic interaction liquid chromatography is a technique, or an acronym certainly, that was first coined and first coined and reported by Andy Alpert in the Journal of Chromatography in the early 1990s. HILIC is a technique that's suitable for the retention and separation of poorly retained compounds in reverse phase chromatography. So typically that is analytes that are quite polar. So they may be polar neutral compounds, or they could be polar ionizable species. Now, the way that HILIC operates as a technique is that a water layer is formed around the stationary phase particles, and analytes can partition into and out of this water layer. There are other mechanisms of interaction also at play with HILIC. There are modes of interaction such as ion exchange, hydrogen bonding, attraction and repulsion type mechanisms too. So this is quite a complex chromatography separation mode. Now, of course, from the stationary phase perspective, we can change the type of column that we use. So we can have stationary phases that are charged or neutral when with different types of properties. And these also affect the weightings of the mechanism in HILIC and also the retention and separation of our analytes. So I think we can safely say that HILIC is truly a multimodal technique. There are multiple modes of interaction to help us with retention and separation. Now, when we consider HILIC as a technique, it is different to reverse phase, which is the most common separation technique that is typically used. Water is a strong solvent, and in fact, the bulk solvent in HILIC is acetonitrile, the aprotic solvent acetonitrile. And most HILIC mobile phases contain a large volume fraction of acetonitrile. So this also helps us form the water layer, which defines HILIC as a technique. Now, it's important that we keep a certain amount of aqueous component to our mobile phase, which is around about 3%, depending on conditions and column chemistry and so on. And this allows us to maintain the integrity of the adsorbed water layer around the stationary phase particles. Now, we can use a variety of different solvents in HILIC mobile phases, just like we do in reverse phase and other techniques. But what's important to note with HILIC is that protic solvents, and those with the ability to hydrogen bond and so on, such as methanol, which is very popular in reverse phase, can disrupt the water layer around the stationary phase particles in HILIC. This leads to poorer reproducibility and retention characteristics of our analytes in our HILIC methods. So a small quantity of methanol can be used, and it can be used quite usefully, for instance, in our sample diluent to help dissolve polar analytes. And also we can use methanol, very small quantities, I'm talking 1 to 2% type quantities of methanol, to help us with our selectivity in our separations as well. So HILIC is defined by having a bulk amount of acetonitrile in the mobile phase. We need an aqueous component to maintain the integrity of the adsorbed water layer, and we can use small amounts of protic solvents such as methanol to help us with solubility of our samples and also to a degree for our separation selectivity. So you can see how HILIC is different to techniques such as reverse phase. So that's a bit about HILIC and the mobile phase system. So when should we, as separation scientists, consider using HILIC? What is the point at which we think, okay, reverse phase isn't quite giving me what I need. I now need to consider other separation modes. Well, first of all, if you know something about the chemical properties of your analytes, such as the log P or lipophilicity value, then this will help you understand whether HILIC could be an option for your separation. So as a general rule of thumb, analytes with a log P of around 0 or less are typically suitable for HILIC. So we can see from the cartoon that's on the screen now, I'll just activate my laser pointer here. So we can see from the scale that I've put here, where we have a log P scale, from around -5 to +5. In the center, we have a log P of 0. And I have 3 model or example analytes. You can see that the compound glyphosate is very polar, non-chromophoric and very polar, and has a log P of -2.39. We can see caffeine has a log P of around 0, and amitriptyline as a model pharmaceutical has a log P of around 5. And from the top here, where I've drawn these lines, you can see that where HILIC, the range of log P that is covered by HILIC, and the range of log P that is covered by reverse phase. So positive values up to 5 and so on are ideal for reverse phase chromatography. Around 0 and down to negative values, HILIC is likely to be an option. Of course, there's a zone of overlap in the center. You can see from around -1.5 to +1.5. And of course, this is application dependent. Sometimes reverse phase may be appropriate. Sometimes HILIC may be appropriate. It really does depend on your particular samples and situation. So that's the first way that you can make an informed call on whether you think that HILIC is suitable or not. But what about those situations where you don't have physical chemical information like log P values? Well, one alternative, which I'm showing on the screen now, is that you can use the retention time of caffeine in a reverse phase system as an indicator of whether HILIC is appropriate or not. So as you can see on the screen with the chromatogram now, we have a simple separation using a standard C18 column. It is a simple gradient from 5 to 100% B in 10 minutes. And you can see that glyphosate has a retention time of around about 1.5 minutes. Caffeine has a retention time of about 6.5 minutes. And amitriptyline is 9.5 minutes. And the general practical rule of thumb that we found in our laboratory is that if your compounds elute before caffeine, such as the example I'm showing here, then HILIC may be suitable. So you can either spike caffeine into your samples and see where it elutes with respect to the rest of the compounds in your sample, or standards, whatever you're using, or you can simply, like on the screen now, note the retention time of caffeine at 6.5 minutes. If your compounds elute before caffeine, then HILIC may be an option. So this is a good practical rule of thumb to help you understand if HILIC is an option for your particular situation or not. So we now know a little bit about HILIC, we know a little bit about the technique, and we know a little bit about when we could potentially consider using HILIC for our separations. So what does HILIC offer us? What are the benefits for HILIC? Well, it can provide the retention and separation of polar compounds, especially those that are purely retained in reverse phase chromatography. So that includes analyte classes such as metabolites or polar pharmaceuticals or pesticides and so on. And they could be polar neutral or polar ionized species. HILIC also provides orthogonal selectivity to reverse phase chromatography. So what do I mean by that? Well, here we have a polar neutral mixture of 6 components. And in reverse phase LC, isocratic analysis, you can see the elution order and retention times of these 6 species. If we look at the same mixture, but in HILIC mode, you can see we get complete reversal of the elution order. So our analytes now elute 6 through 1. So a completely opposite elution compared to reverse phase chromatography. So HILIC can give us quite a different selectivity profile compared to reverse phase. So the advantages of HILIC, so just to move towards finishing this first section of the talk, is very suited for the retention of polar to very polar analytes. And what this means is that we don't need to use additives such as ion pair reagents and so on that we sometimes do in reverse phase chromatography. Ion pair reagents can be notoriously tricky. If you've ever used them, then you'll know what I mean. With the equilibration of the system, the fact that ion pair stick to many things, your separating system, the instrument, vials, and so on. So ion pairs can be quite challenging. You don't need to use ion pair reagents with HILIC. Because we use such a large amount of acetonitrile in our mobile phase as standard in HILIC, it's been shown that we get enhanced mass transfer, which lowers the C term in the Van Diemter equation, which means that we get improved chromatography. And also this high organic content can also help us with certain detection modes, those evaporative type detection modes such as mass spectrometry or ELSD type detectors. The high organic content is ideal for the process of desolvation and ion formation and so on. So HILIC mobile phases can be very useful in these situations. And finally, as well, there are other advantages, but I've listed just a few here. Because we have such a large amount of acetonitrile in our mobile phase, we have a lower viscosity for our eluent. This gives us lower back pressures for our separating system. So this means that we can use higher flow rates, we can use smaller particle sizes, and all the benefits that that gives us to our chromatography. However, it's just as important when we consider the good things, we need to think about the disadvantages of HILIC too. And this is particularly where some of the challenges have come from people trying HILIC for the first time or having bad experiences with HILIC. And the main issue that I've found in talking to many people all around the world, it's down to the knowledge and experience of HILIC as a technique. Typically, it is much, much lower than for reverse phase chromatography. Many of the guidelines and principles that we apply every day for reverse phase chromatography, running methods, doing method development, need to be different for HILIC. And if we try and apply the reverse phase LC principles to HILIC, it can lead to poor chromatography, poor reproducibility, and people getting very frustrated with the technique. In general, the parameters are less well understood in HILIC, and they're still being explored and explained even now. Typically, the stationary phase options are far less than reverse phase. And as I said at the beginning, the operational guidelines are different. And I'll touch on one or two of these later on in the presentation, especially around column equilibration. One of the other challenges with HILIC is that because we use such large amounts of organic solvent in our mobile phases, and typically in our sample diluents, sometimes this can be quite challenging with regards to solubilizing our sample mixtures. It's very odd that HILIC as a technique is ideal for the analysis of polar compounds, but actually getting polar compounds to dissolve in high amounts of organic solvent can be a real challenge. And this is certainly one of the challenging areas for HILIC. And finally, should you be interested in retention modeling and predictive modeling and retention time predictions, the experiences so far have been mixed with HILIC as a technique, and these have been published in the literature by a variety of scientists, where sometimes HILIC predictions have worked well and other times they've worked not so well. So this is still something that's being explored. Now, the purpose of this talk is to focus on the first disadvantage point I mentioned here. That's to try and share some practical knowledge and some practical experience based on the work that's been performed in our laboratory. Okay, so the first topic around HILIC stationary phases. So HILIC stationary phases can be broadly split into 4 different groups. There are acidic phases with acidic character, basic phases that have basic character, neutral phases with neutral character, and there are other types of chemistries which I've labeled here, such as vitionic, and novel type chemistries, which if you read the literature or you Google HILIC on your laptop, you come up with all sorts of strange and weird and wonderful stationary phases that people are using in this interesting mode of chromatography. So it's always useful to consider different stationary phases for method development. And when I talk about reverse phase method development, I say exactly the same thing. The most useful thing is to look at different column characters, just as in reverse phase chromatography, because this has an effect on the elution order and retention properties of your analytes. Typically, it will allow you to get to a method quicker. So here we have on the screen 3 different types of column chemistries. We have an acidic phase, a basic phase, and a neutral phase. And you can see from the table that we've characterized these different phases depending on some of their properties. So we've, for example, we've examined the partitioning of different analytes into the adsorbed water layer. We've looked at anionic analyte interactions and cationic analyte interactions. We've also looked at hydrogen bonding. So this type of characterization is common in the column chromatography world, and such data is available also for reverse phase chromatography. What this does is it allows us to explain how the different properties of the columns have been designed to help with different types of separations. So what does that mean chromatographically? Well, here we have the same 3 columns, an acidic column, a neutral column, and a basic column. And this is a mixture of 9 polar compounds. It contains acidic, basic, and neutral analytes. So a variety of different compounds analyzed under the same conditions on each of the different columns. And we can see the chromatography is different on each of the phases. And in fact, if we pick out, for instance, a neutral analyte, we can see that the change in the retention time, particularly on the acidic phase compared to the neutral and basic phase. If we pick an acidic analyte, we can see again the difference between an acidic, neutral, and basic retention for that particular acidic analyte. And then also for a basic analyte, again, we can see differences in the retention behavior. So what we're seeing under the same conditions is the analytes eluting in different order. The selectivity is different with these different phases. If we look at the elution order, and I've just listed the numbers out there, which you can see the elution order changes. So when we're performing method development and we're exploring our samples to understand where is a good place for us to begin our method development or our method optimization, this type of screening approach can be very powerful. And in fact, column screening is an approach that I advocate strongly in reverse phase and in HILIC method development as well. And you'll see later in this particular talk, I'll talk about a protocol for method development, so a structured way to develop HILIC methods based around a column screening approach. So the 3 phases I just spoke about are listed on the screen there, as you can see at the moment. And there's a lot of detail on that slide, but all I'm trying to do is highlight the properties of the phases. So people are interested typically in the functionality of the phases, the USP listing, the particle size options, the pH range, and so on. So I've included that slide to answer those questions, which is what I normally get asked when I'm talking about a different type of column chemistry. Okay, so let's look at some HILIC eluent parameters. So for instance, pH. pH can be very powerful in chromatography in reverse phase and also in HILIC. HILIC pH, the mobile phase pH, affects your analyte ionization and also the stationary phase ionization as well. And we can see on this particular separation of 6 components with acids, bases, and neutrals. This is on a single column. This is the acidic base column. You can see we get differences in retention time and elution order depending on the 3 different pHs. So pH can be very useful for method development. Of course, if all of your analytes are polar neutrals, then the pH of the mobile phase is probably less influential. If we look at buffer concentration, as a parameter, we can see here, very interestingly, peak 3 is a basic molecule, procainamide. And we can see that as we increase the concentration of the buffer from 2 millimolar up to 18 millimolar, whilst keeping all the other parameters the same, you can see we get a slight change in the retention behavior of the analytes. So the basic analyte, this is on, again, an acidic column. The basic analyte reduces in retention as the concentration increases. What we've got to remember with HILIC, and that's the second point that I'm pointing out here on this slide, is that we need to think about, when we're changing parameters, the effect on the analyte and the effect on the stationary phase, but also the effect of the parameter change on the adsorbed water layer. The adsorbed water layer really is the center of the HILIC separation. And anything that disrupts that adsorbed water layer can lead to retention time instability. But if we change a parameter, such as what we're showing now, when we increase the concentration, we need to think about how does this affect the adsorbed water layer. There might be an effect of the mechanism of interaction, for instance. By increasing the concentration, it's likely that we change the weighting of the ion exchange interaction, the partitioning interaction, and so it's the balance of those two mechanisms that are giving us the differences in our retention behavior. This is the same for reverse phase, of course, but in reverse phase we don't have the adsorbed water layer. Temperature, again, is also an important parameter in HILIC, just as it is in reverse phase. And on this particular separation, this is on a neutral column. You can see that we have an acid, a base, and neutral analytes in this particular mixture. And you can see, interestingly, as we increase the temperature, I'll just turn on my laser pointer tool here. As we increase the temperature, we can see peak 4 here, which is tryptophan, actually increases in retention. And typically when we increase retention, compounds elute more quickly. So there's something different happening for this basic molecule here. And here we can see the polar neutral. We increase the temperature and the polar neutral compound elutes more quickly, which is probably more expected. So temperature is a good parameter to explore in HILIC, as it is in reverse phase, to optimize your separation. So that's a little bit about the parameters in HILIC that are useful. And now I'm going to talk about two key topics. One is column equilibration, and the second is sample diluent. So column equilibration really is important in HILIC chromatography, and I think it's probably one of the areas where many people who have tried HILIC as a technique have had bad experiences or didn't realize the importance of equilibrating their column, and so got poor retention reproducibility or separation reproducibility. This leads to frustration and people thinking that HILIC as a technique is poor and doesn't work, when this is not true. Equilibration in general, no matter what mode of chromatography you're using, is important for good retention time robustness. Now, in reverse phase chromatography, we all know from our experience and from various books that around about 10 column volumes are required to equilibrate a separating system. Typically after gradient analysis is what most people do, around 10 column volumes. And you can see on this graph, I've got on the y-axis percentage equilibrated. This is just a K value. And on the bottom, on the x-axis, I've got column volume. And we can see the green line for reverse phase chromatography. We can see that pretty much after 10 column volumes, you can see that the retention time is quite stable. Now, for HILIC, this is not the same. When we look at HILIC, the blue line, you can see that the amount of equilibration is much more. It takes longer to establish that adsorbed water layer around the particles, and this is particularly true when you buy a brand new HILIC column. The initial equilibration of a brand new HILIC column takes around 60 odd column volumes. This is for a brand new column. That's really important. If you don't do that, then you won't have a fully equilibrated column, leading to consistent retention times. Now, quite Interestingly, once you've used the column for the first time, you've done some separations, it's been equilibrated, you wash the column and then you put it back in the box and you come to it a week later or whenever you next do some HILIC work, the equilibration time is less. In fact, the work that we've done in our labs, when you use your HILIC column for the second and subsequent time, it's only around 20 column volumes are required to equilibrate your column. So what we're hypothesizing is we think that the formation of the adsorbed water layer the first time you use it is important to establish that water layer. Then when you clean your column and you put it back in the box and you use it again, it's already partially equilibrated from that first time you used it. So that means that the number of column volumes needed to get back to steady state is less. And we've tried this with a number of columns and a number of different types of columns, and this seems to be true. It seems to be the case. Now, obviously for isocratic HILIC methods, once you're fully equilibrated, then you get stable retention times. There's no need to equilibrate between injections and so on. If you do gradient HILIC analysis, which I'll show you a little bit later, then you need to consider up to 10 column volumes between injections to get back to steady state. Now, this can be application and condition dependent, depending on the properties of your stationary phase and of your mobile phase. But in general, you need to consider equilibration time between injections of around about 10 column volumes. So equilibration, really very important in HILIC to get reproducible and stable retention times. So what do I mean when I talk about column volume? I've added these two slides in here because I think in column volumes and so on all the time, because I'm dealing with columns all the time. But of course, in the real world, in the real life, people are thinking, how long do I need to equilibrate this column for? People think in minutes rather than column volumes. So what is column volume? It's the amount of mobile phase that's between the particles and in the pores of your HPLC column, and it's a very simple equation that is calculated on the screen as I've put here. It is basically the equation for a cylinder, pi r squared, multiplied by the length of that cylinder, and then multiplied by a porosity value. Now that porosity value depends on the properties of your particles, and I've given the porosity values for the ACE columns on the screen there. The important thing here is these values are specific for ACE columns because of the particles we use and the way that we pack our columns. If you use other vendor columns, then these values may need to be determined, or you can contact those manufacturers for their specific values. Ideally, it's better to experimentally determine these values. It's far more accurate, and those are the data that are on the screen for ACE columns, which I'm showing you there. And of course, column volumes independent of flow rate, because column volumes are a determined, calculated volume amount. But of course, as I said, practically, what does this mean? Because we all think I need to equilibrate my column for 20 minutes or whatever. So for a simple calculation for column volume, you can see on the screen there using the equation I showed you before. So here's the equation that I showed you before, and you can see here I've highlighted across the top, I've got the lengths of column, and down the side I have the column internal diameters, and I've calculated out the volume of columns. And we can see there a 250 by 4.6 column has a column volume of 2.617 milliliters. But what does that mean in time? In this second table, I've recalculated column volumes for different column IDs, and that is the second column here. And then what I've done is applied different flow rates that we would typically use with some of those column dimensions to give us time values. And here in this column, the fourth column, it's for 20 column volumes, and here in the fifth column, it's for 60 column volumes. What I'm trying to illustrate here is if we use the 254.6 millimeter column as an example, you can see the column volume in the second column is 2.617 mils. At a flow rate of 1 mil a minute, it's going to take us 157 minutes to fully equilibrate that column when it is brand new. For the second and subsequent time we use it, it's going to take 50 odd minutes to fully equilibrate that column. So you can see using longer columns that are wider means has an impact on the amount of time it takes you to fully equilibrate the column. If you're fortunate to have UHPLC equipment, you can see here a 50 by 2.1 millimeter column has a column volume of 0.109 mils. At a flow rate of 0.5 mil a minute, which is pretty reasonable for that dimension. You can see it takes 13 minutes for 60 column volumes to fully equilibrate, or 4 minutes for 20 column volumes. So hopefully that table is helpful to put into context and perspective the types of columns you use and the types of equilibration times that we're talking about for HILIC for the first time you use your column and then subsequent times you use your column. So the second topic I wanted to talk about after the column equilibration is sample diluent. So many people struggle with solubilizing their samples for HILIC because of the high amount of acetonitrile typically in the diluent and also in the mobile phase. So here you can see a HILIC N column, a neutral base column, and we have 3 model compounds. We have tyramine as the model base, mandelic acid as the model acid, and hyperxanthine as the model polar compound. And you can see that what I've done is taken different volume fractions with different percentages of acetonitrile and tried to dissolve the mixture of the 3 compounds in each of those different types of diluent and measured the peak shape and the peak height. You can see that, for instance, with tyramine, too little acetonitrile down at low levels here, you can see you start to get peak splitting, whereas too much acetonitrile, we can see here in 100% acetonitrile for the polar neutral, and we don't get any solubility at all. Now, the type of stationary phase can also play a part in your peak shape for your chromatography, not just the solubility. So, for instance, here we have the acidic column, and we can see that potentially we've still got some issues with tyramine here, but also the acid now possibly suffering from overloading effects on the acidic column down at low amounts of acetonitrile. And then finally, on the basic column, the acid and the polar neutral look reasonable, but the base here you can see again at low amounts of acetonitrile, there's a bit of splitting, which is probably more to do with solubility. So the recommendation that we're making for people who want to explore which is the best diluent for their particular samples is that you have to try a few of these different combinations. I can't think of any better way to recommend it. We're recommending between 20% acetonitrile and 80% acetonitrile. In the example I've shown on the screen, it's in 20% increments to explore the solubility of your samples for HILIC because of the high amount of organic that's used in the mobile phase. So some general hints and tips. This is quite an important one. I think this is a really good one. It's just as applicable for reverse phase as it is for HILIC. And you can see here that we have mobile phase and mobile phase A and mobile phase B. The concentration here is actually different in each of the 2 different mobile phases because we've made this up as distinct volume fractions. So for mobile phase A, we've made up 96% acetonitrile and added 4% of a 10 millimolar buffer. So this gives us a low concentration. When we make up 50% acetonitrile, 50% buffer in mobile phase B, obviously it's a very different concentration. Now this concentration difference can cause us real problems in our chromatography. So the best thing to do is to match your buffer concentration in mobile phase A and in mobile phase B. These ionic strength gradients give very poor retention reproducibility, especially in HILIC, because of the effect on the adsorbed water layer. But actually, even for reverse phase, it's good practice that you should match your concentration in mobile phase A and in mobile phase B. So just a couple of other hints and tips. I'm not going to go through these in detail as we're slowly running out of time, but you can see here that we have comments about balancing the buffer concentration, equilibration of your first time you use your column, and then if you're doing gradient between the injections. If you use high amounts of water in your sample diluent, this can cause problems with peak shape. You can use protic solvents in your mobile phases and diluents, but be aware of the disruption of the water layer. And it seems really obvious, but using inorganic salts can cause you precipitation issues. Also, if you use iron pairs in your mobile phase or your diluent, this can also disrupt the water layer too. And the recommendation that we make for ACE HILIC columns is to store them in IPA to maximize the column lifetime. So I'm going to go through in 2 minutes the method development now that I've finished the first part, which is a very brief overview of HILIC as a technique and some practical hints and tips. So this equation is the resolution equation, and really what this equation tells us is how important selectivity is in chromatography. This is the same for HILIC as well as reverse phase. Now the selectivity can be affected by changing your mobile phase, but also your stationary phase. And as I said earlier, I'm going to show you a column screening approach, which I think is the most systematic way to do method development. Now here we have an overview of method development, and first of all, assess your analytes. What do you know about them? Do you know anything about their solubility? Do you know their log P values, their structures, and so on? This can help guide you with your phase choice and your mobile phase choice. Secondly is to do some scouting runs. For HILIC, we recommend 3 different pH values on 3 different stationary phases using a gradient run. You can then stand back and look at the data and choose one of those different options to optimize further. Step 3 is your optimization. Should it be gradient or isocratic analysis? Do you want to tweak your retention properties through your percentage organic? Do you want to modify the buffer, the temperature, and so on? And then typically, depending on the industry you're in, you would then validate your method, and then you would perform sample analysis, or you would transfer the method somewhere else for sample analysis. So we've developed a protocol for method development, which you can see on the screen now. So it's a bit small. I apologize, you can't see all the detail, but you can certainly see the slides afterwards and look at it in as much detail as you want. And the great thing about this protocol is we've also produced a poster. So if you want a free poster that has this protocol and some of the other information that I've talked about today, there's contact information at the end. You can send us an email and we'll send you this free poster through the post. So I'm going to follow this systematic protocol to develop a method very quickly. So the mixture I'm going to look at is a polar neutral mixture. It's basically a method for the determination of caffeine and some of its related substances. So we can look at the log P values because we know these are very well described substances, and we can see the log P values are all around about 0 or less. So it's likely that these will be suitable for HILIC. But if we look at this, first of all, we challenge ourselves, is HILIC necessary? This is a separation using a standard C18 column. Our general rule of thumb, do our compounds elute before caffeine, which is peak 1? Yes, they do. So potentially HILIC is a suitable technique for this method development activity. This protocol and screen I'm going to use, we're only going to use 2 of the pH values for this particular screen because the mixture is polar neutral. All of the compounds are neutral. So I'm only going to use pH 3 and pH 4.7, which is not going to have much effect on the analytes, but will have a small effect on the stationary phase, which may help us from a selectivity perspective. So here we can see the gradient screens. We've got the 3 different columns at pH 3, and we can see the separation and behavior of the analytes. We can see here the principal component caffeine and the other 4 related substances on the HILIC A column, the HILIC B column, and the neutral column. If we look at the pH 4.7 separation, we can see some similarity at the different between the different columns. But also there are some differences which may give us options with regard to developing a method. And in fact, for this particular method development activity, we took the HILIC neutral separation at pH 3 and developed it further. So firstly, should we develop a gradient or isocratic method? Well, if we look at the differences between the two, the left-hand side is gradient, the right-hand side is isocratic, we can see that we've got a challenge, because the isocratic analysis, we can't get the separation of peak 2 and 3, the critical pair, and we're beginning to lose, due to band broadening, peaks 4 and 5. So for this particular example, gradient chromatography was still our best option. So we can perform further further optimization, had a quick look at temperature. By reducing the temperature down to 15 degrees, as expected, we would improve the resolution of the critical pair. And this was the final method that we actually used, because we actually gave this to somebody else for some work that they were doing. So we can see here we have finally the principal components, caffeine, and we had the related substances. So peaks 2 and 3 here were not quite separated, but the customer was happy to drop a perpendicular and quantify these two compounds from the chromatography here, and then peaks 4 and 5 were baseline resolved. So just to bring that together and complete this webinar, hopefully you've heard something useful about HILIC today. HILIC provides the retention and separation of polar analytes, typically those that have poor retention in reverse phase chromatography. HILIC can be mechanistically complex, but most chromatography is. What we have to consider with HILIC is the adsorbed water layer. The disruption of this layer can cause problems with reproducibility. I've explained and described a screening protocol, which we have available in a book and on a wall chart, a poster, sorry, for you to look at. This is a systematic approach to method development in HILIC. We also have something similar for reverse phase coming out soon. Selectivity is very important in chromatography, in HILIC and in reverse phase, hence why the different column chemistries that I showed today. And the two key topics really to try and make HILIC a success: consider your equilibration time for your column, make sure it is long enough, and then secondly, try and get the best sample diluent to solubilize your analytes, but without affecting your peak shape.